great pleasure to introduce Kevin to you all. I guess I came to know Kevin about 3 years ago when he took the second semester physics, aka lower division electricity and magnetism. Last fall, he came to my office. He asked me, do you have something that I can do as my capstone? And at that point, I was teaching 2 intro-level mechanics labs. And one of the things we did always was to study the dynamics of collision by using 2 moving cars. And something that really puzzled me for quite some time, because one of the things we did was what we call elastic collision. And so if you know that physics about elastic collisions, you should know that, hey, the kinetic energy should be conserved, total momentum should be conserved. But when students turn in their work, almost like half of the class are basically telling me you're wrong, because my data shows total kinetic energy is not conserved, and here's my data. And I felt like this is a really big puzzle. So I told Kevin, hey, this is something that we really should be looking into, and he accepted the challenge. And in the next 10 or 12 minutes, he's going to show you what we did, how we really tackled this issue. So I'm sure that in the future, the work we're doing here is going to really benefit students who will be taking that intro-level mechanics lab class. And also want to mention, Kevin is graduating this fall, and his plan is to really become a science teacher. So I really, we wish you the best, and don't forget to send some of the students our way when you graduate. All right, the floor is yours.
Hello everyone, my name is Kevin Vasquez. My advisor for this presentation is obviously Dr. Hung Tao Shi, and today my presentation is going to be on how to improve the collisions lab here at Sonoma State University. So here's a brief outline of what I'm going to be talking about. We got definitions, motivation, the equipment that I've been using this past semester, data acquisition and analysis that are coming from me and Dr. Shi's 2 physics mechanics labs, and my conclusions. So like I said, before I get into the whole process on what I was doing this semester, I just want to give you guys some brief definitions on what the things I did. So what we have on the images right here, we have 2 images of elastic collision versus inelastic collision. And as many of us know, an elastic collision is when kinetic energy and momentum are conserved. But for an inelastic collision, it's quite different because kinetic energy is not conserved while momentum is. And right there underneath, we got 2 images. So image 1 is the elastic collisions part, where we got 2 balls. The red ball and the blue ball, when they collide towards each other, they go back towards the separate ways. But for an inelastic collision, it's quite different because when we see the blue ball going towards the red ball, it continues to go with it. So after that, we have formulas that I have used this past semester that is very helpful throughout this process. And first off, it's kinetic energy. What is kinetic energy? Well, kinetic energy is an energy that a body possesses by being in virtue of motion. And what the formula is, it's Ke equals 1/2 mass speed squared. Next, we got momentum, and momentum is the quality of motion of a moving body that is being measured by its product of its velocity and mass. So for that, we have momentum equals mass times velocity. Now, this right here, the percentage difference, is the most important formula because this is what gives us our percentage value. So we got delta equals total momentum after minus total momentum before, divided by total momentum before times 100. Now you may be asking, why am I only talking about momentum? Well, I'm not, because it's also used for total kinetic energy. So what we'd be doing again was delta equals total kinetic energy after minus total kinetic energy before, divided by total kinetic energy before times 100. Next, what's my whole purpose on doing this? Well, as Dr. Shi said, physics department here at Sonoma State University offers 2 physics mechanics labs, Physics 116 and Physics 209A, where students run this head-on collision experiment. what I'm doing for this project, I'm focusing on the elastic collisions part. And how Dr. Shi said earlier on, both total kinetic energy and total momentum have to be conserved. However, when Dr. Shi gave the students the exact same equipment and lab process, they were getting it wrong. They were getting 20 to 30% when we're looking for 5%. And that's how we wanted to know what are some of the reasons why students are causing these answers. And I'm going to be doing, is there like any way to improve the students' lab experience? Next, we got the equipment that I've been using this past semester. We got 2 carts, 2 flags, clamp, launcher, 2 photo gates, 2 cores that connect to the photo gates and the Pasco Scientific, a weight scale, and 2 computers. And this image right here, we have 3 generations of flags that we have been using for this project. We got cardboard, aluminum, and the newest one, a 3D printed. Now, why are these important, you may ask, the flags? Well, these flags are being measured for the speed of the cart. So, what I did this past semester before clamping it down was making sure the track is on level because it reduces the vibrations. Also, after that, what we then do is when we pull the lever on the launcher, cart 1 passes the first photo gate and the flag touches the infrared beam, which gets our first data point, which then cart 1 pushes cart 2 towards the second photo gate where we get our second data point. And we then use Capstone program coming from the Apple computer, which then I then use my own computer on an Excel sheet to get the values of like total momentum, difference of total momentum and difference of total kinetic energy before and after the collision. Right here is just a quick demonstration on what I just said. So I pulled the lever. You obviously see that the cart 1 is past the first photo gate, then it then pushes cart 2. Don't look at how it fell in the back because students have a thing that blocks it so it won't fall off the track. But as you can see, everything has to be close together because if it isn't, our percentage value is really going to be high. So this is my set of data. What I did first was I did this without a clamp. I ran the cart 1 10 times to see if our initial velocity for cart 1 is consistent. As you can see, it is not. We got from 30 all the way to 90. We want it to be a straight line as possible. So this is without a clamp. We obviously in the corner right there, we have the masses of our carts. For cart 1, we got 0.507. Cart 2 is the exact same, 0.507. We then have our initial velocity for cart 1, which is V1I, Then V2F, which is the final velocity for cart 2. And my data points for that was 0.92 and 0.70. But as I shown earlier, without a clamp, it's all over the place, and we're not able to get the right data for it. So our percentage difference for total momentum is 8.74%, and total kinetic energy, we got 30.56%, which is what we don't want. We want the 5% and below. So what Dr. Shi said after was add a clamp, and let's see if there's a major difference or not. There's a major difference from what we've seen. We can see that it's straight as line as possible. I did this 10 times, and 7 out of the 10 times, I was able to get 0.74, which is good, which is a good consistency. As I said earlier on, we got the masses of the 2 carts. I got 0.74, 507. Then for the mass of cart 2, I got 507 as well. For my initial velocity for cart 1, I got 0.74. My final velocity for cart 2, got 0.69. My percentage difference for total momentum is 2.52, and my total kinetic energy is 4.41%. So that means we were actually able to get to that 5%, which is great. I thought I did well, but now we're gonna see what else happens. What are some of the things that students may get the reasoning of 5 and above? So what me and Dr. Shi have observed from entering the 2 physics mechanics lab is students don't often pay attention to the small details. As you can see, the photo gates are far apart from each other, which doesn't really work. We want them as close as possible. Also, when pulling the lever on the clamp, sometimes it goes super slow. Even though there's friction, it goes super slow. We want that, but we want the photo gates to be close as possible in order for it to work. So, here is the data that I've gotten from 2 physics mechanics labs from Dr. Shi. When we told the students to clamp down the track and run 10 trials, students were actually able to get the consistency as well. The red data is from physics 209A, straight as possible. Their masses of the carts was 0.511, mass of cart 2 was 0.508. Their initial velocity for cart 1, they got 1.96, and their final velocity for cart 2, they got 1.94. And their percentage difference for the total momentum is 4.9, and their total kinetic energy was 2.55%. Great. We want that. We need that from everyone. Now, we also have from Physics 116, consistency again. We have the masses of their carts. They're quite similar to Physics 116 as well. But their initial velocity for cart 1 is 0.41%, and their final velocity is 0.40%. So, what is their percentage difference that they got? They got 3.39% for total momentum, 4.76% for total kinetic energy. Great. What we needed. My conclusions for this is when we 3D printed this, it helped greatly. We got the results. And when clamping down the whole track, it reduced the vibrations significantly, which got us the answers that we were looking for. And well, due to the friction, the photo gates have to be placed as close as possible. Because if it isn't, we're going to be seeing percentage differences of total momentum and total kinetic energy of 20 to 30%. Lastly, when we combined the total amount of groups from Physics 116 and 209A, there was a total of 23 groups. 6 groups were actually able to get to that 5% or below, while the others have dropped the percentage to 10 to 20%, as before when it was 20 to 30%, which is great significantly. Lastly, I want to say thank you to all the professors here, Dr. Target, Dr. Steverson, Dr. Miller, Dr. Hong Taoshi. They've seen me grow, they've seen me cry sometimes as well. But I also want to say thank you to Ryan, because without him, these 3D printed flags wouldn't be possible. My friends, my family, even my classmates, because without their support and feedback, I wouldn't be able to give you guys this presentation. So thank you.
All right, questions for Kevin? Yeah.
I have a question. Did you talk to some of the students in the class? Do you know what they felt when they were doing an experiment and wouldn't get the results that sort of leading them?
Yes, so when I attended those 2 classes, me and Dr. Shi would walk around, and any student would ask me, they would tell me, they would just give me the answer, what do I need? And I'm like, nah, I could help you out a little bit, just I gave them the percentage difference formula, and I also told them, you know what, try the whole process again, and let me see if you guys are missing something in small detail that they were missing.
Can I ask a question for the flags? So before you did this, were they actually using the cardboard ones?
The cardboard one was used 2 to 3 years ago.
Oh, okay. So
Then
they were using the metal ones?
Then they used the aluminum ones, and then recently this semester, Ryan has 3D printed them.
Yeah, and you found those were much better than using the metal ones, right?
Yes, they were.
Any final questions for Kevin? If not, then let's thank you.